The students, here is a problem on indeterminate beams and solved by superposition method, particularly the application of the area moment diagram. So by superposition method, determine all support reactions. EI is constant. Construct the shear force and bending moment diagrams and sketch the elastic curve. So because one support is fixed, so let's select this as the moment center. And first, let's have the moment diagram for the uniform load of 36 kilonewton per meter. So the value here is equal to 36 times 6 times moment arm 3, and that is 648 kilonewton meter. And it is a second degree curve, parabola, this one. Then for the moment of this triangular load up to section C, the moment is 1/2 of 3 times 36, and the moment arm is 1/3 of 3, so 1. So 1/2 of 3 times 36 is 54. 54 times 1 is also 54. So this is 54 kilonewton meter and third degree. And the moment at the point D here, so since the equivalent concentrated load is 54, imagine that there is 54 here, and the moment of that 54 kilonewton load farther at D is 54 times 6, so that's why we have an extension here of 324 kilonewton meter. So therefore, the moment diagram for this triangular load at D would now be this whole three different areas. Then finally, the moment of this 30 kilonewton load is 30 times at B is 30 times 60. Then at D is 30 times 12. So the total distance is 12. So 30 times 12 is 360. Then later on, we will divide this portion between B and D as two. This is a trapezoidal area, so we divide this into two triangles as shown. Because this part is not considered in the calculation of the deflection at B or at C. So imagine that supports B and C are removed, so this becomes a cantilever beam. We can compute the deflection at B, and by definition, it is equal to the deviation of point B relative to the tangent at B. That is automatic also the deflection, because the reference tangent at D is horizontal. The vertical deviation of B relative to the tangent at D is also interpreted as the deflection at B. So imagine that B and C are removed. So it is expected negative because the deflection is downward. So I'll just put it negative EI delta B, or negative EI deviation of B relative to the tangent at D. So beginning with this area, the area is 1/3 6 times 648. Since this is 6 over 4, the distance of the centroid from D is 6 over 4 or 1.5. The distance of the centroid from B, because this is moment of area between B and D with respect to B, so the point of reference is B. So this is 4 plus 6, 10. 10 minus 1.5 is 8.5. So that's why the moment arm here is 8.5 for that area. Next, for this area here, it is between B and D also. The area is 1/4, 3 meters times 54. 1/4, 3 times 54. This distance is 3 divided by 5, or 0.6. Therefore, the distance of the centroid from B is 4 minus 0.6. 4 minus 0.6 is 3.4. So that's why the moment arm here is 3.4. Then For this rectangular area, the area is simply 6 times 54. 6 times 54. The centroid is here, 3 meters, half of 6. 3 plus 4, 4 is 7. So that's why the moment arm here is 7. Next, for this triangle, the area is 1/2 6 times 324. This is 1/3 of 6, 2 meters. So the distance of the centroid of this triangle from B is 8 meters. 10 minus 2, because that is 2 meters, 1/3 of 6. So 8 meters. Next is this triangle here, the smaller one. The area is 1/2 of 10 times 60, 1/2 of 10 times 60. The distance of the centroid of the triangle from B is 1/3 of 10, so that's why it is 10/3. Then plus this remaining triangle, 1/2 of 10 times 360, and this distance is 2/3 of 10. The centroid from B is 2/3 of 10, and 2/3 of 10 is 20/3. Therefore, EI delta B is negative, combining these values here, negative 34,197.7 kilonewton meter cube. So I will not show the units anymore. And it should be in kilonewton meter cube. So likewise, we evaluate EI delta C, which is expected negative also. Remember, it becomes a cantilever beam, and this is the deflected shape. The deviation of C relative to D is the deflection at C, and by definition, it is also negative EI deviation of C relative to D. And it is the moment of areas between C and D with respect to C. So we just focus ourselves with the areas here and compute the moment of these areas with respect to C. So beginning with this area here, 1/3, 6 times 648. Since this is 1.5, the distance of centroid from C is 6 minus 1.5, so 4.5 meters. And plus this area here, which is rectangle, 6 times 54. Moment arm is 3. 6 times 54 times 3. I hope you can follow. Next, plus this area, 1/2 of 6 times 324. This distance is 2/3 of 6, or 4, which is that. Then, for this trapezoid here, by the way, this is 180. 180 is 30 times 6. So 30 times 6, 180. Then we divide this trapezoid into two triangles. This triangle here has an area 1/2 of 6 times 180. 1/2 of 6 times 180. And the distance of the centroid, which is here from C rather, is 1/3 of 6, which is 2. And finally, for this area, 1/2 of 6 times 360, 1/2 of 6 times 360, this distance is 2/3 of 6, so 4. So computing EI delta C is negative 16,092. So likewise, we apply the reactions, unknown reactions, RB and RC. For RC, the moment at the wall D is 6 RC times 6, so that's why we have 6 R sub C, and that distance is 6 meters. Then for the moment of RB, RB times 10, 10 RB at B, and at C it is just RB times 4, so we have 4 RB here. Then that's the moment diagram by parts due to these reactions. So these reactions will cause the cantilever beam to deflect upwards like that. So if we compute the deflection at B, which is positive this time, due to the reaction at B, then it is just the deviation of vertical deviation of B relative to the tangent at D, and interpreted from area moment principles, interpreted as the moment of areas between B and D with respect to B. So these are the areas, and for the first area here, 1/2. So EI delta B due to the reaction is also EI deviation of B relative to D. So 1/2 of 6 times 6 RC. This distance is 2 meters, 1/3 of 6. Therefore, the distance of the centroid from B is 8 meters. 8 meters is 10 meters because that is 10 meters. Distance BD is 10 minus 2, so 8. Then for this entire triangle, the area is 1/2 of 10 times 10 RB, and the distance of the centroid from B is 2/3 of 10, 20 over 3. So computing EI delta B due to the reaction is 1000 over 3 RB plus 144 R sub C. So likewise, EI division of C relative to D is automatic EI delta C due to the reactions because the reference tangent, as I said, is horizontal at D. And this is the moment of areas between C and D only. So this is the area between C and D. We have trapezoidal part for this part here and triangle. So this trapezoidal part is divided into two triangles so that it's easy for us to compute for the moment arms with respect to C. This is point C. So EI delta CR is equal to, for this area, 1/2 of 6 times 6 RC. The distance of the centroid from C here is 2/3 of 6, so that's why it is 4. And for this area here, 1/2 of 6 meters times 10 RB, and 2/3 of 6 again is 4. And finally, for this area, 1/2 of 6 times 4 RB, this distance is 1/3 of 6 or 2 meters. So combining like terms, EI delta CR is 144 RB plus 72 R sub C. So delta EI delta CR plus delta BR, EI delta BR plus EI delta B should be 0 because the supports do not settle. So, but if we transpose EI delta B to the right, it becomes positive. So that's why EI delta BR here, which is 1000 over 3 RB plus 144 RC, is equated to EI delta B transposed to the right, it becomes positive. So equals 34,197.7. Call that equation 1. Then EI delta CR plus EI delta C equals 0. So that means EI delta CR equals the positive of EI delta C. So 144 RB plus 72 R sub C is equal to 16,092. Solving these two equations simultaneously, we obtain RB equals 44.42 kilonewtons and R sub C is 134.66 kilonewtons. Then, if you want to solve for the reaction at D, we consider the entire system, summation forces vertical equals 0. So RB 44.42 plus RC, which is 134.66, plus R sub D, which is 120.92, plus RD equals 30 plus this triangle here, 1/2 3 times 36, plus this rectangle 36 times 6 or 6 times 36. So R sub D is equal to 120.92, which is that kilonewtons. Then considering ABC, assuming M sub C is positive, that's the positive sense of moment at C, just consider ABC. There is shear at C just to the left, but if you sum up moment about C, it will not be involved. So M sub C, counterclockwise positive, plus the moment of this triangle, which is 1/2 of 3 times 36 times 1, 1/2 of 3 times 36 times 1, plus moment of 30 kilonewtons, 30 times 6, then equals R sub B, which is 44.42 times 4. So from there, we can solve m sub z negative 56.32 kilonewton meters. Then likewise, considering CD to solve for MD, that's the positive sense of MD. Let's assume positive summation of moment about C equals 0 because we have solved already RD. So M sub D plus 120.92 times 6 equals M sub C, which is this, M sub C, negative 56.32, then plus the moment of the uniform load, 36 times 6 times 3. So solving for MD, it is equal to negative 133.84 kilonewton meter. Then we sketch the shear diagram, moment diagram. We construct the shear force and the bending moment diagrams and sketch the elastic curve on the next slide. So here is now the shear diagram. So beginning with downward negative 30, shear diagram in kilonewtons, negative 30, then constant plus RB, which is 44.42. So from B to D here, constant, then minus 1/2 of 3 times 36. So it is negative increasing. The value is 14.42 minus 1/2 of 3 times 36. So that's negative 54. 14.42 minus 54 is negative 39.58. Then plus 134.66. So 95.08. Then minus 36 times 6. We have negative 120.92. So that's 120.92. So it closes. This area, this distance can be solved by similar triangles, or the shortcut is shear 95.08 divided by the uniform load, which is 36, so 2.6411 meters. Therefore, this distance is 6 meters minus 2.6411 meters, so 3.3589 meters. So you can compute this area easily because these are just triangles. Those are the indicated areas. 125.558 kilonewton meter, and this is negative 203.079 kilonewton meter. So here we have to set up the shear equation for BC in order to find this distance x1 where the shear is 0. Although this area 1 here can be solved by just area of parabola, which is 2/3 base times side. But it's for area 2, we can analyze this, but the best way is to use the shear equation and use integration to compute for the area, the better, because your calculator is capable of computing areas by integration. So to solve for x1, we set up shear equation for BC, and it is 14.42 minus the area of this triangle. Now, if I call this distance x1 from 0 load, by similar triangles, imagine this is W. W as to x1 equals 36 as to 3. 36 over 3 is 12, so that's why this is 12x1, the intensity of the load. So 12x1, therefore the shear in BC is 14.42 minus this area 1/2 of x1 times 12x1. And we equate it to 0 to solve for x1 because we want to find this point where shear is 0. And solving for x1, it is 1.5503 meters. Therefore, area 1 is either 2/3 of 1.5503 times 14.42, because that's a parabola. The tangent at this point is horizontal, zero intensity of the load. Or it is integral of the shear equation dx1. So this is the shear equation, 14.42 minus 6x1 squared. Then dx1, and that area is 14.903 kilonewton meter. Likewise, area 2 is integral from 1.5503 to 3 meters. If you look at the figure, then it is negative 25.643 kilonewton meter. So we are now ready to sketch the moment diagram. So beginning with this zero moment at A, then minus 30 times 2, so negative 60, then plus 14.42 times 1, so negative 45.58, straight line. Then we have positive decreasing area 1, so negative 45.58 plus area 1 of 14.903. So this is positive decreasing curve. So negative 30.677 kilonewton meter plus area 2, which is negative 25.643. So it is negative 56.32. Take note that the moment at C is negative 56.32 kilonewton meter. So that's checks. Also, moment at B is negative 60, negative 30 times 2. So it checks. So negative 56.32 plus area 3, which is 125.558, we have positive decreasing curve. So 69.238. And finally, 69.238 plus negative 203.079, negative increasing curve, negative 133.841. And that's the moment at the negative 133.840 kilonewton meter. So the very, very small discrepancy is obvious because of rounding of values. So it closes. Then we project these points because these are the points of inflection, points where concavity changes direction. So for this part, the elastic curve is concave down. So from A to this point, concave down, in fact up to here, concave down. This is the elastic curve through the support because the supports do not settle. Then up to here. Then here, positive moment means concave up elastic curve. Then here, negative moment, concave down elastic curve through the support. So that's it for this video. I hope that you were able to follow the explanation and the solutions.